Right, so the next thing I'd like to discuss is conditional probabilities. Okay, so this is the idea when you know that something has happened and you want to account for what the probability of something else happening is. So first I'll talk about this at a little bit of a high level. So remember that we sort of had in our mind that if we did an experiment, we looked at the number of experiments that we'd done, okay, and then we divided it by the number of times an event had occurred, okay, and we did that for a lot of experiments, so they should get closer and closer to some number, and that number was the probability that that event occurs, okay? So it's the probability of the event. Okay, so now let's consider a specific experiment. Let's suppose our experiment is an experiment that consists of pulling two cards from a deck, one after the other. Okay, so consider the experiment of taking two cards, okay, without replacement from a deck of 52 cards, okay? And let's consider the event, two events, okay? So event 1 will be the event where we get two aces, okay? So the probability of ace and ace, okay? So the first card is an ace and the second card is an ace, right? And let's also consider the event of just getting an ace for the first card, okay? So this is the event, let's say, that the first card is an ace, right? Well, the probability that the first card that you get is an ace is, well, 4 out of 51. Oh, sorry, 52, because there's 52 cards in the deck, okay? Then, if we think of ace, ace, well, we can count the number of ways that you can take two aces out of a deck and divide that by the number of ways of taking two cards out of a deck. So the number of ways of taking two cards out of a deck are 52 times 51. There's 52 things you can do to take out for the first card, and then 51 cards remaining for the second to take out. Okay. Similarly, the number of ways you can take an ace and then an ace out is 4 times 3, 12. There are 4 cards you can take out for the first, and once one card has been taken out, there's 3 that you can take out for the second card. Okay. Now, we could think of this as sort of the idealized limit if we kept taking 2 cards out of a time out of a deck, and then we did it again, we took 2 cards out of a deck, and then we did it again, we shuffled again and took 2 cards out of a deck, and we just kept on doing this forever. The proportion of time which you expect to get ace, ace is this, and this is the proportion of time that we expect to get just a single ace, okay, on the first attempt. Okay, so now let's suppose we're asked a slightly different question. Suppose we asked that given the first card is an ace, what is the probability the second card is an ace? Okay. We're going to give a special notation for that. We're going to say what's the probability of ace, of an ace and an ace given next card is an ace. So this sort of parallel line here in the probability means given or conditional on the first card being an ace. What is a probability that we actually get two aces? Okay. So let's think about what that sort of means philosophically. Before, remember, it was sort of the number of experiments divided by the number of times that the event that we're interested in had occurred. Now when we're saying given, we're sort of looking at, well, the number of times that we get ace and ace, but not relative to the number of experiments that have happened, but given the number of times that just an ace has happened for the first card. Okay, like this. Right? So if we look at all the times that we've got an ace from dealing two cards, and that's what proportion of those times, okay, do we get ace ace out of that hand, okay, then this, as the number of experiments gets really, really large, should go towards some number, and we can call that the probability of ace ace conditional on the first card being an ace. Okay, so that's good for giving a definition, but it doesn't give us a way of sort of calculating maybe what this is in terms of our normal probabilities. Well, one thing notice we can do is we can divide this by something that we know about. We can divide by the number of experiments that have happened so far, okay, and then times by the number of experiments that have happened so far. This cancels out, okay, like this. Right, so we've just times and divided by the same constant, by the same number, the number of experiments that we've done so far. So as the number of experiments here gets bigger and bigger, this is going to converge to the number of aces divided by the number of experiments. Okay, and this is going to converge to the number of times we've got two aces divided by the number of experiments. Okay, so in total, what's going to happen here is, well, this is going to go to the probability of ace and ace. Okay, because we know that if we look at the number of times our ace-ace event has occurred and divide by the number of experiments, it converges towards the probability. Okay. Similarly, this is going to converge to 1 divided by the number of experiments. Okay. So we can imagine that as this gets bigger and bigger, it's going to get closer and closer to 1 divided by the probability of an ace. Okay. Right. This might become a little bit clearer when you've done a little bit more about limits, but you can imagine that this number is going to get closer and closer to this number, and this number is going to get closer and closer to this number. So then we could say here, in this case, that, well, the probability of an ace and an ace given an ace is equal to the probability of, we get an ace for the first card and an ace for the second card, divided by the probability of an ace for the first card. Okay? So that's sort of roughly what conditional probabilities are. They're really ratios between different probabilities. Okay? But they represent what would happen if we did an experiment a large number of times and focused on, okay, the number of times that the outcome that we wanted happened relative to the number of times that the event we conditioned on had happened. Okay, so that's sort of the motivation for the following definition. Okay, so we can define the conditional probability Okay, so for two events, E and F, okay, the conditional probability of E given F is probability E given F, which we're defining to be equal to the probability of E and F divided by the probability of F. Okay, so one little bit of notation here. When I write these two dots next to an equal sign, what I'm saying is I'm defining this number to be this. Okay? Alright. And notice we're saying that if we look at all of the times that F has occurred, okay, then within those, what time did E also occur? Right? So that's what this is representing. One thing to notice is that, well, sometimes probabilities can be equal to 0. Okay, so this definition is only going to be valid if the probability that F, this event, is positive. Okay? And in some sense I could let this be equal to whatever I like if the probability of F was equal to 0. Okay? But the convention is that by convention the probability of E given F is taken to be 0 if the probability of F is equal to 0. Okay, so that's just sort of the normal convention that we work with for this. Okay, right. So let's just consider a few kind of examples just to get an idea. All right, so just to kind of get the intuition a little bit more of what conditional probabilities are. Okay, so here's a quick example. So suppose we have a study. This is taken from a real example that I read in a newspaper. Okay, so a study of, say, 250 75-year-old men. There's a study of 250 75-year-old men. Okay, and they essentially asked them in this study if they ate fruit or not. Okay, and they also tracked them over the next 10 years and saw which people died over the following 10-year period or not. Okay, and the results were as follows. So if we draw a Venn diagram, we let A be the people who lived 10 years more, on this side of the Venn diagram, and B whether they ate fruit or not. Okay, we get some numbers. So let's say in A we had 62 people here who lived 10 more years but didn't eat fruit, 100 people who both lived 10 more years and ate fruit. We had 50 people who ate fruit and didn't live 10 more years, and then 38 people here who didn't live 10 more years and didn't eat fruit. Okay? And then you can start to ask questions like, what is the probability, given this sort of data that we have, this information, the probability that you live 10 more years given you eat fruit? Okay, so then from this we can do the calculation for that. We look at the total number of people that eat fruit. Okay, so in this case 150. Okay, and then look at the proportion of these, okay, that live 10 more years, which is 100. Okay, and then we get 2/3. Okay, really what we're saying here by probability is that we're saying if we chose one of these people at random, what is the probability that they live 10 more years given they ate fruit. Okay, so really the experiment that we're doing is out of the 250 people listed here, let's suppose we choose one at random, what is the probability that person lives 10 more years given they ate fruit. Okay. Further, we can look at the probability that they live 10 more years given they do not eat fruit. Okay. And so if we look at the people who do not eat fruit, okay, so that's everyone outside of here, there's 100 of those, 62 plus 38, okay, and 62 of those, okay, live 10 more years. Okay, so here we've got about sort of 0.67 roughly, and here we've got 0.62. Okay, so this is actually, well, the numbers here aren't actually the data from this experiment, but there was a study that actually looked into this, so you can look at the various factors, okay, conditional on your different lifestyle, and then come up with an estimate for the conditional probability that you live for a further period of time. Okay. All right. So sometimes probability can be a little bit unintuitive, and the following example that I'm going to give, okay, is one instance of that. Okay. So let's suppose I tell you that given I have a brother, I ask you what is the probability, okay, and I'm telling you that I have two siblings as well. So given I have a brother and I tell you I have two siblings, okay, what is the probability I have a sister? Okay. So given I have a brother, I have two siblings. Given I have a brother, what's the probability that I have a sister? So you can think about that for a second. And most people's gut reaction to this question is that it's a half, because, well, you can either have a brother or a sister, so the other one must be either a brother or a sister, so it's 50-50. Okay? But actually, if we think about this properly, we'll actually see that it's 2/3 probability. Okay? So let's look at this. So the state space for this is brother, brother. Okay, so first sibling a brother, second sibling a brother. Okay, or brother, sister, first sibling a brother, second sibling a sister. Okay, or sister, brother. Okay, first sibling a sister, second sibling a brother, and sister, sister. Okay, so first sibling a sister, second sibling a sister. Okay. Alright, and we want to calculate the probability of a sister given I have a brother so what we're looking at is the probability of a sister and a brother given the probability I have a brother. Okay, and I can calculate the probability to have a brother, the probability to have a brother, assuming that it's a 50-50 chance between having a brother or a sister for any one individual child. Okay, then there are 3 events here that correspond to me having a brother. Okay, so there's a 3/4 chance, so this guy is 3/4. Okay, and if I look at all the events in here where it's brother and sister, there's 2 of those. Okay, So in this, it's 2 quarters, okay, of these events. 2 out of 4 events are brother and a sister. So notice, by doing this conditioning, I'm essentially eliminating, okay, the outcome where sister-sister can occur, and then looking at the proportion of those, okay, which have a sister and a brother associated. So we're going to get an answer of 2 quarters divided by 3 quarters, which is equal to 2/3. Okay? So that can come across as a little bit sort of counterintuitive at first, okay? But really, what's being asked here is the reason this is sort of unintuitive is because I haven't specified again the order at which that brother occurred. Okay, so I could slightly change the condition. So let's change the condition a bit. Example continued. Okay. Let's say that now I have my 2 siblings, and I say given the first, let's say the first being the eldest, is a brother. Okay, what is the probability the second is a sister? Okay, so well, the state space is the same here, okay, but if I want to do the calculation now, probability second sibling is a sister, given the first is a brother, okay, notice I'm considering just 2 parts of this sample space, yeah? There's brother, brother, or brother, sister, okay? So half the time the first is a brother, okay? And only one of those times do I get a second sibling being a sister. So 1 out of 4. And so we get the answer that you'd expect, a half, okay? Now the difference that's occurred here is we've moved from a situation where the event of having a brother, okay, is not independent of the event of having a sister, okay, to a situation where the event of having a brother as the first child has no effect in principle over the having a sister as the second sibling, okay. So what's introduced here is some notion, okay, of independence, and that's also what you were sort of anticipating with this question, okay. So here, just to kind of write this down a little bit, in the second answer, here, meaning this answer, the outcome of having a brother as the first sibling does not affect the chance of the second sibling being a sister. Okay, this sort of notion of not affecting something, okay, is what we call independence. Okay, the idea that having a brother as a first sibling is independent of the second sibling being a sister. Okay,